What's going on, guys? It's the Unhinged Engineer here, and unless you've been living under a rock, you've probably heard two things about artificial intelligence. For one, it's revolutionary and it's unlike any piece of technology we've ever seen before, and number two, it's going to revolutionize just about every industry of professional work and even aspect of our personal lives. You've probably heard all the hype. I'm not going to get into the hype in this video. What I do want to talk about in this video is the specific impact of artificial intelligence on aerospace engineering. I'm a young engineer, an aerospace engineer specifically, and going into my career, it's really important to realize how is the way in which we're going to work going to change over the next however many decades as artificial intelligence becomes more and more ubiquitous than it already has become in the last few years. And so in this video, I'm going to take a look at AI's impact on my industry, specifically of aerospace engineering, and hopefully try to understand how I can make the most of it and how we can make the most of it to our professional advantage. And so if you're interested in content that helps you succeed professionally, then this is the channel for you. I'm the Unhinged Engineer. I make professional development content about all the aspects of engineering careers that they don't really talk about in school. And on top of that, I'm talking about all these dynamics of professional success as I learn them in real time as a young person. I didn't figure all this out 20 years ago. And so if this is the kind of content that you're interested in, then I highly recommend you like, comment, subscribe. But enough beating around the bush, let's get right into this video. So there's two things I want to talk about here. For one, I want to talk about adoption curves, and probably not in the way that you're used to. I want to talk about not just how individual people come to terms with and ultimately adopt into their lives emerging technologies, but some of the dynamics around how specific industries may differ from one another throughout that adoption process. That's the first thing I'm going to talk about. And the second thing I'm going to talk about is, okay, now that we understand the context of how AI is being adopted into aerospace, what are the trends that this adoption has started to cause? I'm going to highlight some trends that I've seen in my experience as a working professional in this field, so that again, hopefully we can hop on this bandwagon, learn to harness these technologies, or at a minimum, even if these technologies and these themes aren't the hot, sexy thing in a few years, we at least have experience and context on the specific ways in which AI is manifesting itself, so hopefully we can figure out what the next one is. But let's talk about adoption curves before we get into that. So you've probably seen an adoption curve laid out something like this, right? So this is like a probability distribution function where this is time on the y-axis and this is number of people, right? It's a distribution of people. And right here we have the average time to adoption plus or minus some standard deviation. And typically the way this is discussed is in the earliest 10% of adopters, these are our early adopters, right? These are people who have the highest risk appetite. They just want to try the cool stuff. They don't care if it's expensive. They don't care if it's unpolished. If you've seen somebody walking around Times Square with an Apple Vision Pro on, they're probably an early adopter of AR technology. On the back end, this bottom 10%, these are the laggards. These are people who will not adopt a new technology until it's absolutely necessary for whatever reason, right? And these are the people who, still show up to work today. They don't have a ChatGPT account. They've never used it before. Maybe they're skeptical. Maybe they think it's gonna kill everybody. Who knows? It's people who are still holding on for dear life and not adopting AI or any other technology. And then this middle, 80% here, these are the masses. These are most people in a given field, right? And I would say artificial intelligence is probably somewhere here, right? At this point, AI is very mainstream. It's got a lot of institutional investment. It's got a lot of institutional push. Employers are trying to encourage people to use artificial intelligence, and even schools held on for dear life in the beginning, right? They weren't adopting AI and they were trying to prevent people from using it. Even schools are starting to get on the bandwagon and let students use AI. The point I'm trying to get at is, we're kind of in this position where AI has newly entered the mainstream and we're kind of seeing the dynamics of how it plays out within the middle 80% of people. So we're beyond that early adoption phase where these technologies all kind of sucked and people only use them in the absolutely most visionary ways. And we're not yet towards that ultimate saturation point where everybody and their mother, kids grew up after artificial intelligence, right? We haven't yet hit that point. So this is a probability distribution function where I think for the purposes of this video, it gets more interesting is if we lay out a cumulative distribution function, which would look something like this, right? And so we still have time on the x-axis, but we have a percentage here now. And now it's gonna look something like this. It's a little steep. Something like that, right? Where this is 100%, And we get this inflection point, let's say around here, at 50%. This inflection point is really interesting. Two things here. For one, it's the point at which we've made it over the curve. Like a lot of technologies never actually get here and kind of die out before they can ever really hit that kind of saturation point, that critical mass, and ultimately become ubiquitous as things like the internet have. That's number one. Number two, I want to talk about the dynamics of how this inflection point shifts based on certain factors, right? So the point at which something really hits critical mass and really is here to stay, for lack of a better word, this point in time is going to be different for different technologies. And that's what I want to talk about. I've decided to lay this out kind of as an acronym. I'm going to call it TAR, like tar as in sticky tar, as in how sticky is something as it comes to mainstream. Three things. First one is talent. Put simply, like, are there people in this field of study that have the talent required to adopt these technologies? The second one here, I'm highlighting as advantage. Is there actually an advantage towards adopting this technology? Another way to say it would be applicability or usability. Is there a lot of bang for the buck in terms of, okay, once we adopt artificial intelligence, we're going to have an advantage over our competitors, over our adversaries, etc. The stronger that advantage would be, the more demand there's likely to be for its adoption. And the last one would be risk. This is a really interesting one, especially in the case of aerospace engineering. The riskier fields and the riskier applications of artificial intelligence are naturally going to be more reluctant to adopt just about anything, especially AI, for several reasons. If there is a field with a lot of inherent risk to it, people have a much more defensive posture as disruptive technologies come into the market. And thus, that adoption curve, this inflection point is going to shift, this way. Right? It's going to shift to take longer and longer in time as compared to something with lower risk. So let's lay out a couple of examples. Let's say this is our baseline. Let's talk about SaaS businesses. So SaaS businesses, they're really trying to provide a good customer experience and maintain their clients. Beyond that, there isn't a ton of risk. It's not a life and death scenario for SaaS, as much as people on LinkedIn might try to convince you otherwise. So SaaS might look something like this. Pretty early on, this would be, now slightly riskier than that, you might say, okay, here's traditional finance, like hedge funds and banks. Because now we're risking a lot more money, especially these are people's money and they have a fiduciary responsibility to not mess it up. But nonetheless, like, people are not dying quite yet, right? This isn't a life and death scenario. It's just money. Now, beyond that, now we're getting into more of the danger zone. Like, let's say here, I would put probably aerospace engineering somewhere here. Like, this is a point at which there's physical systems involved. In defense applications, these physical systems might have munitions. In aviation applications, they might have like live people on board, like 200 people on a Boeing airliner. The stakes are much, much higher. Probably some of the highest. And then maybe like only exceeding that would be something like biomedical technology, like outright pharmaceuticals. This is the point at which, okay, we're putting like drugs into people, they're consenting to treatment, we better not kill anybody. High stakes, and there's lots and lots of regulation. Like, something to note is that risk typically leads to more regulation as well, which is probably for the best most of the time. And so if you think about SaaS and chatbots, like, that probably has the least amount of regulation as compared to something like drug discovery. There's a hell of a lot more to do with the FDA there. And so all I'm trying to get at is, in terms of AI's adoption, aerospace is probably one of the slower ones because the risks are incredibly high and the demand for predictable, reliable performance is incredibly high with aerospace as compared to other things you might see on the news like chatbots and SaaS businesses and hedge funds and all that stuff. Even within aerospace, okay, now let's take the aerospace baseline and try to like divide things out even further. So this is baseline aerospace. On the front end, this might be like commercial UAVs. So these things, they're inspecting bridges, they're inspecting oil pipelines, and obviously at the end of the day, the customers want the products to perform well, but this isn't yet a life and death situation. Beyond that, maybe towards the middle here, this is where you're getting UAVs for like defense. And I would say, yes, obviously there's a ton of risk involved with UAVs for defense, but the counterpoint to that there is there's a lot of advantage to having autonomous drones versus human pilot drones or other things. We'll talk about that in the trends section. So even though like you're probably thinking in your head, man, UAVs for defense are still pretty damn risky, maybe they should be further along, the advantage is so high that the adoption of this technology has been really, really quick. And towards the back end here, you might have something like actual space, like satellites, right? Putting things in orbit that are actually running on artificial intelligence. You don't want to lose that, right? And then probably at the tail end here, you would get something like aviation, like a Boeing airliner with 200 souls on board. You know, you really don't want that AI model to mess up. And there's been lots and lots of tragedies in the past of automation systems in airliners going haywire and unfortunately leading to the deaths of lots of people. So this is probably the highest risk adoption here that's going to take the longest naturally. And in addition to that, this kind of freaks people out, but 90% of any given flight trajectory is already done on autopilot. So what's the advantage going to be, that incremental advantage using something non-deterministic like a neural network when we have autopilot and traditional control systems that we've tested so rigorously and we know work already? Like that advantage is probably very low as compared to something like UAVs for defense. So again, even within this one subfield, that inflection point is going to wiggle a lot. So what are the key points I'm trying to get at with talking about this? For one, aerospace is probably slow in terms of adopting AI technologies just because the risks are higher than other fields. If you go online and you're looking at new companies in like fintech or again, SaaS businesses or whatever else, you're going to be seeing them adopting AI technology really, really quickly, and then go to an aerospace company and it's probably taking longer. And the reason is because the risks are higher. So counterpoint to that for us is we're earlier, like we're further ahead in the game. Sometimes I might see people on LinkedIn who got into artificial intelligence like 10 years ago. And I'm thinking, man, I wish I was that person. Granted, I was pretty young at the time, but man, I wish I was that person and I got into the AI game way before everybody else did. That's a huge, huge advantage. But with aerospace, we do actually have more of an advantage than somebody who's trying to get into chatbots in 2026, right? The chatbots market is way, way more saturated than something like aerospace engineering, right? So that's probably closer up here. You get what I'm trying to get at here. The second point, that things fluctuate within aerospace. For certain fields, it might be slower or faster than others. And so think about yourself and think about where you are in your career. Do you want to be like on the cutting edge, like working on these aspects of artificial intelligence that are taking the longest because the risks are highest? In those kinds of fields, you're going to be focused a lot more on the reliability aspect versus in these fields in which it's much more ubiquitous already, maybe you're focused on operation and integration with other systems, right? Like you're really getting after it. You're getting in there, deploying these systems in the real world because they're further along this adoption curve versus something on the back like this might be more R&D. So just something to think about there. Okay, so we've talked about like the dynamics of how aerospace is adopting artificial intelligence and why it might be slower than other fields, and there's lots of fluctuations within aerospace as a field because aerospace actually has a lot of different subfields within it. Now let's talk about some of the trends I've seen as a working professional in terms of artificial intelligence in aerospace. I'm going to lay out three here. One is edge computing. The next one is reliability, for reasons we just discussed. And then the last one is digital twins. Just three kind of large macro trends I've seen that are really interesting and I've tried to get into as much as possible. I would say specifically for myself, just as a sidebar, these two are the ones I focus on the most. The digital twins are also really interesting, and I know people work in that area. It's pretty cool stuff. But let's start off with edge computing. So edge computing is pretty simple. Let's say you've got a drone, and let's say you want to do some cool artificial intelligence. Traditionally, you've got some kind of database, this might be on the other end of the world. Let's just assume it's not. The drone is collecting data and is beaming that data down to, or up, whatever, to some kind of, database or supercompute, whatever, right? Not on the vehicle. That's going to then crunch some numbers, do some math, and it's going to upload commands to the drone to tell it what it can or can't do. Maybe these are commands written by a human, maybe they're generated by some algorithm running on, on this compute, right? The point is, like, this loop here has both latency and security concerns. So focusing more on the latency, because that's just what I know the most about, honestly. This is slow. If a drone is flying itself, in a very like aerobatic way or very fast, you have to make these decisions incredibly quickly. And a lot of times these latency requirements just can't be met by over-the-air transmission, plus the time it takes to actually run the algorithm, and then that over-the-air transmission back in terms of commands. A lot of times it's just too damn slow, and then there's security concerns, like somewhere along the way the signal can get intercepted, decrypted, whatever. And so it's very advantageous to say, okay, let's do this on board. So we got this drone again. We've got compute on the drone instead of on the ground. We collect data, send it over wire to our computer, crunch some math, send commands back out to the drone. Like, there's none of this loop here. There's none of this loop. This goes away. And we're just doing everything. This is on board or edge compute. That's the central idea, right? And so there's lots of different things to think about here. For one, how big are our models? Another one, how fast is our hardware? Another one, have we made this model generalizable enough that we can trust it to make decisions autonomously? And while this is more of a reliability concept, it's worth mentioning here, because a lot of times in order to get the kind of range of distribution you need, a model's naturally going to have to be bigger, and then that causes problems, and you kind of get this, coupled requirements issue that can be very, very bad and make deploying edge compute systems very, very difficult. And so this area is incredibly, incredibly rife with opportunity and ongoing research. So this is probably my favorite amongst the three. I find it really interesting. And yeah, that's a big macro trend to talk about. For reasons we discussed earlier, we can't just let an AI model, an agentic thing, whatever, just kind of go hog wild and do whatever it wants. Like, we need some checks and balances in there, whether they're human checks or automated checks, something like that. And this is where you get into stuff which we would typically refer to as like an autonomy stack. And what this stack means is that there's different levels to the autonomy. And those levels could be defined by anything from the scope of the decision being made, to the amount of time in which it has to be made, to whether or not a human needs to be involved in it or something that's automatable. A stack implies that there's like a hierarchy of systems that make different checks and balances on one another. Different companies take different approaches to this. Like, some companies, it's just everything is a neural network. And if we have this autonomy stack, like, this is a neural network, this is a neural network, this is a neural network, and then this is a neural network. And all that this stack is really doing is piping requests and results up and down between these different neural networks. That's a very, very deep learning oriented stack. But what other companies might do, or researchers, whatever, might do, is say, okay, we're going to have a neural network to the lowest level of control, and then at the highest level of control, we're going to have some kind of finite state machine, or a decision tree, or a human in the loop, right? Stuff like that. So this would be kind of like the neural network is doing the lowest level, and it's just kind of being regulated by, maybe the state machine determines when to switch between one neural network versus another. Or this decision tree says, okay, like, based on certain conditions, I'm going to trust a neural network more or less than other conditions. You could also have like an opposite thing. This is maybe like a classical control algorithm, like, this is navigation, and this is guidance. And then at the highest level, you have kind of a neural network to really just act as like this translation layer between a human operator and everything else. So this is kind of like, we're doing the lower levels of operation in a more traditional way, like this is traditional GNC. And then at the highest level, we're making large context window decisions with a neural network and a human usually in that loop, hopefully. So there's lots of different ways in which, we can kind of structure these stacks, and this is a very, very ongoing area of work. And then even within the levels of the stack, you can say, okay, like, how do I detect anomalies? Like, how do I know when my models are failing me? Similarly, kind of talking about that, like, distribution robustness. Like, how can I ensure that my model is generalizable as possible and can operate in a wide range of operational contexts like a human would? These are all different areas of study in autonomy reliability. And one more I throw in here is interpretability. Like, okay, diagnostically, how can we actually make sense of what a model did, and probably more importantly, why it did what it did. These are all ongoing areas of research that are really, really cool. Last one to talk about here, digital twins. So usually when you're doing some kind of like training, like you look at your system, you look at your drone, and you kind of figure out like, okay, what are the system requirements, figures of merit, what is the environment that I'm going to be operating in, usually some kind of like equation of motion or dynamics to describe that environment. And then you're running training like in this loop pretty statically. Like you train, you deploy a model, and depending on how that goes, you restart this cycle. This is a pretty high latency static thing. Like it takes time to run this training and then deploy it and test it out in the field and then ingest those results and train it again based on the findings and stuff like that. Well, what if we had like a physical representation of drones based on live real world data? Like we have these things out in the field and they're actively collecting data and sending it back to our digital twin. The digital twin is like running some kind of training and then it's sending things back all in real time. What I'm trying to get at here is this is more of a constant iterative thing that requires live data coming from a real world system. And so if you have like a fleet of systems, like in Tesla's case, they have a fleet of vehicles that are constantly generating data, then you can do this kind of digital twin architecture where you're just constantly running this loop over and over and over again. There's no stop and start as you would have in traditional kind of simulation, which training is just a derivative of in the AI sense. So this kind of live, constantly iterating system based on a virtual replica, so this would be referred to as a virtual replica, and this is a real system. These are called digital twins. And this is another really interesting area of study of how we can automate these kinds of systems to get us more dynamic and more adaptable models and systems than the traditional way of doing it. So in conclusion, what are the main things I want to talk about today? For one, aerospace has a while to go because it's pretty slow in terms of adoption. So if you're trying to get into the AI space and you're interested in aerospace, this, honestly, you'd have more of like a first mover advantage than maybe in some other fields. Like, again, not to bang on chatbots too much, but they're just a great example. The other one is that within aerospace, things do fluctuate a lot. And so, maybe it's the opposite thing where it's like you're really, really diehard about aerospace and you're kind of, you're interested in AI and you don't really know where to start. Depending on where you want to be in that adoption curve that we talked about, that can determine what fields you may be more or less inclined to pursue research in. And then the last one is the trends, and three kind of macro trends I've seen that are really, really cool is edge compute, reliability in general, and digital twins. So these are all interesting areas of research. In terms of specific areas of work, I'm sure there's plenty to talk about. I'll definitely make more videos on them as they come up. But yeah, these are the three that I've seen the most in my life and I find really, really fascinating and have enjoyed working on directly or at least adjacent to. So yeah, this is a bit of a longer one, but I hope you enjoyed. Like I said, I'm the Unhinged Engineer. I make professional development content for other engineers like myself who are kind of early on in their career and trying to make the most of the just about 40 years we have to kick some ass and take some names. Yeah, I'm an aerospace engineer by trade, but I also make videos relevant to all areas of engineering or even STEM writ large. Again, if you're a young person trying to figure out how to navigate your career, which for the most part isn't really taught in school. So yeah, if this is content you're interested in, definitely like, comment, subscribe. Thank you so much for watching, and I will see you next time.